Monumental pyramids and temples stand without any modern technology. Their existence relies on a lost world of ancient machines, ingenious devices that powered entire civilizations. We are about to uncover how levers, ramps, and complex pulley systems built wonders that defy explanation. By the end of this journey, you will see human history through a completely new lens. How did Roman engineers lift stones weighing tons with only ropes and wooden cranes? What forgotten secret allowed the Egyptians to move blocks hundreds of miles? This exploration reveals the brilliant minds who turned simple physics into lasting monuments. What does true innovation look like when you have nothing but raw materials and creativity? An ancient machine, in its purest form, is a brilliant deception against nature's rules. It is not about gears and engines, but about a simple, profound idea, making the impossible possible through clever design. These were tools that amplified human strength, turning a single person's push or pull into a force capable of moving mountains of stone. The core principle that powered every one of these devices was mechanical advantage. This is just a technical term for a simple but magical concept, getting more work out with less effort going in. Think of prying a heavy rock loose with a long, sturdy branch. That branch is a lever, and it allows you to lift a weight your bare hands could never manage. You are not becoming stronger, you are becoming smarter. The lever, the inclined plane or ramp, and the wheel and axle, these are the fundamental building blocks, the alphabet from which all complex ancient machines were spelled out. They emerged from a deep, intuitive understanding of physics. Long before the equations were ever written down, engineers worked with the materials they had: wood, stone, hemp rope, and copper. There were no steel cables or hydraulic pistons. Their genius lay in arranging these simple elements in ways that conquered immense forces. This foundational knowledge is what allowed a civilization to lift a 100-ton obelisk into the sky or drag a 10-ton block for hundreds of miles. It set the stage for every monumental achievement that followed, and it all begins with the most universal tool of them all, the humble lever. A single worker, using nothing more than a long wooden beam, could lift a stone that would otherwise require a dozen strong men. This was the everyday magic of the lever. Its principle is timeless, a beam and a pivot point known as the fulcrum. The closer the heavy object is to that fulcrum, and the longer the end of the beam you push down on, the greater the force you can exert. Archimedes understood this power completely when he declared he could move the earth itself with a lever long enough and a place to stand. This was not mere boasting, but a statement of physical truth. In the quarries of Egypt, workers slid levers under the edges of colossal blocks, using smaller stones as fulcrums to crack them free from the bedrock. On Roman construction sites, these same principles allowed engineers to make precise adjustments to marble columns weighing many tons, gently nudging them into perfect alignment. The lever was more than a tool, it was a fundamental extension of human capability. It turned impossible tasks into manageable ones, not through brute force, but through brilliant geometry. This simple machine saved countless hours of labor and prevented untold injuries, making the construction of temples and aqueducts a practical reality. Its influence extended far beyond the quarry, appearing in the simple balance scales of the marketplace and the devastating force of a catapult's throwing arm. It is difficult to overstate its importance. Without the foundational idea of the lever, the entire trajectory of human construction and invention would have been profoundly different, slowing our progress for centuries. Yet, while the lever could lift, another machine was needed to move these massive weights across great distances. This brings us to the second fundamental innovation, the inclined plane, or as we more commonly call it, the ramp. But the real power of the ramp lay in its deceptive simplicity. A single worker could never lift a 1-ton block straight up, but that same worker, pulling on a rope, could drag that very same block up a long, gentle slope. The inclined plane works by trading distance for force. Instead of fighting gravity directly in a single, impossible vertical lift, you spread that effort over a much longer, sloping path. The steeper the ramp, the harder the pull, but the shorter the climb. The longer and more gradual the slope, the easier the pull becomes, transforming an impossible lift into a manageable, steady drag. For the pyramids, this meant building colossal earthen ramps that snaked their way up the growing structure. Some theories suggest these were straight ramps built directly against one face, while others propose a more ingenious spiral ramp wrapping around the pyramid itself, a sloping roadway to the sky. Workers, likely using sledges and pouring water to reduce friction, would haul the stones along these paths, a slow but relentless procession of human effort guided by brilliant physics. This same principle transformed mountainsides into fertile farmlands through terracing, creating level steps that prevented erosion and made the impossible task of farming a slope into a sustainable reality. Look closely at any ancient structure that soars upward, and you will likely find the ghost of a ramp, the cleverly disguised slope that made it all possible. But lifting and dragging are only part of the story. The true revolution in movement came with the mastery of circular motion, the birth of the wheel and axle. The wheel and axle brought motion to the ancient world. Picture the first potter spinning clay on a rotating disc, her hands shaping something new and symmetrical with an ease that hand building could never achieve. This was the core of the machine, a wheel fixed to a smaller central rod, the axle. When force was applied to the wheel, it spun the axle with tremendous leverage, turning a heavy rotational task into a smooth, manageable motion. Historians trace its origins to Mesopotamia around 3500 BCE, not for transport but for crafting pottery. This single invention unlocked a cascade of others. Soon, the potter's wheel gave rise to the cartwheel, a development that reshaped entire societies. For the first time, a single ox could pull a cart loaded with hundreds of pounds of grain or stone, distances that were once unimaginable for trade or construction. This was not just about moving faster, it was about moving more, fueling economies and connecting distant cities with a reliable flow of goods. In workshops, the principle was adapted into lathes for wood and metal. An artisan could turn a piece of wood against a sharp tool, creating perfectly round table legs, symmetrical bowls, or intricate decorative columns with a level of precision that defined entire artistic styles. The secret to its efficiency was friction, or rather, the reduction of it. By concentrating the point of rotation onto a narrow, polished axle seated in a lubricated housing, the machine minimized the grinding resistance that would otherwise make turning a large, heavy wheel nearly impossible. This simple yet profound mechanical relationship became so fundamental to advancement that the wheel itself evolved into a universal symbol of progress and fate across countless cultures. But why did some advanced societies, like the Inca of South America, build sprawling empires without the wheel for transport? Their mountainous terrain made carts impractical, so they prioritized other innovations, like an immense network of roads and bridges for foot traffic and llamas. This reveals a profound truth about ancient technology. Its form was always a direct response to the environment and the needs of the people. The real engineering genius, however, emerged when these simple machines began to work together. A single rope threaded through a grooved wooden wheel could transform a back-breaking lift into a manageable pull. This simple combination gave birth to the pulley, a machine that conquered gravity not with raw power but with clever redirection. The fundamental principle is one of direction. A person pulling down on a rope is using their own body weight to assist the effort, a far more stable and powerful action than trying to lift something upward with your arms alone. The pulley changes the direction of the force, making the work ergonomic and efficient. But the real breakthrough came with the compound pulley, a system of multiple wheels or sheaves working in concert. Here, the magic of mechanical advantage reached new heights. Each additional wheel in the system multiplied the lifting force, allowing a small team to hoist weights that would otherwise require 100 men. The Greek scientist Archimedes famously demonstrated this power. He is said to have single-handedly pulled a heavily laden warship from the water and onto the shore using a complex arrangement of pulleys, astonishing onlookers and proving the staggering potential of this simple machine. On the vast construction sites of the pyramids, while ramps did the work of horizontal movement, pulleys were likely the key to vertical ascent. Evidence points to their use in raising blocks through tight, vertical shafts within the pyramid's core, a task where a long, sloping ramp would have been impossible. This technology did more than just move stone. It revolutionized safety and logistics. A controlled, steady hoist was far safer than precarious maneuvers with levers and ropes, and it required a much smaller crew, freeing up labor for other critical tasks. The pulley's influence extended far beyond the quarry. It was essential for drawing water from deep wells, for raising and lowering sails on the mighty ships that connected the ancient world, and even in the simple theater, rigging that lifted actors playing gods onto the stage. Its fundamental design is so perfect that it remains utterly indispensable today. Look at any construction crane, the elevator in a building, or even the blinds on a window, and you are seeing the direct legacy of those first ropes and wheels. Yet, while the pulley was a master of lifting, the next machine on our list was a genius of both lifting and holding, an elegant spiral that changed everything: the screw. A spiral turning within a hollow tube could lift a river into the sky. This was the elegant genius of the Archimedes Screw, a machine that conquered gravity not with a pull or a push, but with a continuous, gentle twist. While its invention is famously credited to the Greek polymath Archimedes, the core idea likely emerged even earlier, in the fertile river valleys of Egypt and Babylon, where the constant challenge was moving water uphill. The design was deceptively simple. A helical surface, like a giant screw thread, was enclosed inside a watertight cylinder. One end of the device was lowered into a water source, like a river or a flooded mine shaft. As a worker turned a handle, the entire spiral rotated. With each turn, the screw's chambers would scoop up a pocket of water at the bottom, carry it up the length of the cylinder, and then pour it out the top. It was a continuous, reliable flow, a mechanical staircase for liquid. This single invention revolutionized two critical areas of ancient life: agriculture and mining. For farmers, it meant they could lift water from the Nile or the Euphrates directly to their irrigation canals, transforming sun-baked, arid land into lush, productive fields. For miners, it was a lifeline. As they dug deeper for precious metals, groundwater would flood their tunnels. The Archimedes Screw allowed them to pump this water out, stage by stage, with multiple screws working in sequence to lift water from profound depths. This made previously inaccessible mineral wealth reachable, fueling entire economies. Its construction from wood or bundled reeds meant it was inexpensive to build, easy to repair, and durable enough to last for generations. This was not a machine for kings and monuments, but a tool for the common person, a practical solution that elevated daily survival. The enduring power of its design asks us a compelling question. In a world increasingly concerned with sustainable resources, could this ancient, energy-efficient method of moving water find new life in modern irrigation and water management projects? The screw was a master of lifting water, but it was not the only ancient answer to that vital need. Another machine, far simpler in its motion, performed the same essential task for thousands of years. A farmer stands at the riverbank, his hands on a long pole. At one end, a clay bucket dips into the Nile. At the other, a heavy lump of mud acts as a counterweight. With a gentle push down on the rope, the bucket rises, full and heavy, and with a smooth swing, he pivots the entire device to pour its contents into a waiting irrigation ditch. This is the Shaduff, a machine of perfect balance that transformed the back-breaking labor of irrigation into a manageable, rhythmic task. Its genius was in its simplicity, a lever with a movable counterweight that allowed one person to lift hundreds of gallons of water a day from a source lower than their fields. This was not a machine for monuments, but for survival, turning the seasonal floods of great rivers into a consistent, life-giving supply for crops. The Shaduff first appeared in ancient Mesopotamia and along the Nile around 2000 BCE, and its design was so perfectly suited to its purpose that it spread across Africa and Asia, remaining in use for thousands of years. Its repetitive motion, the dip and swing and pour, became the heartbeat of agricultural life, a symbol of rural perseverance. But beneath that simple rhythm was sophisticated engineering. The farmer could adjust the counterweight based on how full the bucket was, fine-tuning the balance to minimize effort. This single tool dramatically increased the land a family could farm reliably, directly impacting food security and allowing populations to grow and thrive in arid regions. It was a brilliant answer to a fundamental human need, proving that the most impactful machines are often those that ease the daily burdens of ordinary people. The Shaduff's balancing act is a quiet testament to ancient ingenuity, a lever that supported civilizations. This mastery of balance and rotation found another, more permanent expression in a machine that could shape the very bones of history from wood and stone. A wooden column spins rapidly before the artisan's eyes, his hand steady as a sharp tool meets its surface. With each pass, a perfect spiral groove emerges, a shape of impossible symmetry that no hand could carve alone. This was the power of the lathe, a machine that harnessed rotation to bring precision to the ancient world. At its heart was a simple yet profound concept, spinning the workpiece against a fixed cutting tool. This reversed the usual relationship between human and material. Instead of a craftsman moving a chisel around a stationary block, the block itself did the moving, rotating on a central axle powered by a bowstring pulled back and forth, or later, a foot-operated treadle that freed both of the worker's hands. This continuous, uniform motion allowed for the creation of forms that were perfectly round, perfectly identical, and intricately detailed. In the workshops of ancient Egypt, we find evidence of lathes used to turn the legs of chairs and tables, producing sturdy, matching components for furniture that graced the homes of nobles and pharaohs. But the lathe's influence stretched far beyond the Nile. In ancient India, master craftsmen used them to shape delicate stoneware and ornate metal vessels, their surfaces etched with patterns that reflected a deep understanding of rotational dynamics. In China, lathe work on jade and hardwoods demonstrated a technical skill that bordered on artistry, creating objects of both utility and profound beauty. This machine was a quiet revolution in manufacturing. It enabled a form of mass production long before the industrial age, standardizing architectural elements like pillars, balusters, and stone vessels so that they could be replicated reliably and assembled seamlessly into colossal structures. The precision it offered did more than speed up work. It elevated the entire craft, allowing for artistic styles defined by flawless curves and geometric perfection to flourish across empires. The evolution of the lathe itself, from the simple bow-driven model to the more efficient foot-powered version, directly reflected the growing demands of both art and industry, a drive for greater efficiency and more complex expression. Yet, while the lathe shaped the bones of civilization from wood and stone, another machine was responsible for shaping the land itself, moving earth on a grand scale to feed the people who built it. That same principle of rotation that powered the lathe was harnessed to break open the earth itself. A farmer guides a wooden plow, its sharp tip slicing a clean furrow into the soil as a team of oxen strains against their yoke. This was not merely a tool, it was the machine that built civilization from the ground up. Before the plow, societies were largely nomadic, dependent on the unpredictable bounty of hunting and gathering. The invention of the plow anchored humanity to the land, transforming wild landscapes into ordered fields and making large-scale, reliable agriculture possible. The earliest versions were simple digging sticks, little more than pointed branches dragged through the soil. But around 3000 BCE, in the Fertile Crescent of Mesopotamia, a revolutionary design emerged, the Ard plow. This was a sturdy wooden frame with a sharp, pointed share that could cut a furrow without simply skimming the surface. It was a machine for creating fertile seedbeds, and it dramatically reduced the labor needed to prepare a field for planting. The next great leap came with the moldboard, a curved blade attached behind the share. As the plow moved forward, this blade would lift the cut sod and turn it completely over, burying weeds and crop residue to decompose and enrich the soil. This single innovation supercharged soil fertility, allowing the same land to be cultivated year after year with dramatically improved yields. The consequences were monumental. Reliable food surpluses meant that not everyone had to farm. This surplus allowed for specialization, giving rise to artisans, priests, soldiers, and governors. It fueled population growth and the rise of the first cities. The plow did more than just feed people, it forged new social structures. It defined concepts of land ownership and inheritance. It entrenched labor roles and, tragically, often fueled the demand for forced labor to work the vast estates it made possible. Its design evolved slowly over millennia, from wood to tipped with bronze and finally to iron, but its fundamental principle remained unchanged. It makes you wonder, in an age seeking sustainable food sources, what can we learn from the ancient understanding of working with the earth rather than simply dominating it? The plow shaped the societies that would go on to shape the world, and just as this machine carved order from the soil, another set of tools was needed to carve immortality from stone. Granite yields not to brute force but to a precise, focused blow. The chisel and hammer were the ultimate expression of this principle, a machine in miniature that translated human muscle into the power to shape the very bones of the earth. In the hands of a master craftsperson, these simple tools became instruments of profound artistry and engineering. A copper or bronze chisel, struck with a stone mallet, could fracture a block of granite along a nearly invisible fault line, following the stone's own hidden weaknesses. This was not random hacking, but a controlled conversation with the material. Egyptian artisans, working with nothing but these basic tools, created statues with meticulously carved facial features, intricate wigs, and hieroglyphs so sharp they seemed to have been pressed into soft clay. Roman engineers used the same method to shape the keystones for their monumental arches. each block a precise wedge that locked the entire structure into place, capable of supporting aqueducts that stretched for miles. The effectiveness of this entire process hinged on two things: the hardness of the metal and the deep, intuitive skill of the worker. A dull chisel would simply bounce off the stone's surface, while an unskilled strike could shatter a block destined for a pyramid's core, wasting months of labor. This knowledge was a sacred craft passed down through generations, turning raw stone into legible history. How did the development of metalworking enhance the capabilities of these stone-cutting tools? The answer lies in a relentless pursuit of a sharper, harder edge. The progression from soft copper to tougher bronze and finally to hardened iron was a revolution in miniature. Each advance allowed crafters to work faster and on harder types of stone, to carve deeper details and achieve a flawless finish that has endured for millennia. The legacy of the chisel is the legacy of civilization itself, etched into every surviving temple, statue, and obelisk. It was the final, defining touch that turned quarried rock into a message for the ages. Yet, while the chisel shaped local stone, another machine was needed to connect these local achievements into a global network, carrying ideas and goods across the open sea. This brings us to the sail, a machine that harnessed the wind itself. A vast, empty sea transforms into a bustling highway with nothing more than a sheet of cloth. The sail is a machine that captured an invisible force and turned it into motion, connecting continents and fusing cultures long before the modern era. Early mariners, from the Phoenicians to the Polynesians, did not simply drift with the currents. They became masters of the wind itself, hoisting sails woven from reeds or heavy linen, mounted on sturdy masts. Their genius lay not just in the sail, but in its manipulation. By adjusting the angle of the yardarm, they could capture breezes from the side, even from directions that seemed to push them backward, a technique known as tacking that turned the Mediterranean and the Pacific into predictable, if challenging, roadways. This was not blind luck, it was a science born of acute observation. Ancient sailors memorized the rhythms of seasonal winds, like the reliable Artesian winds of the Aegean or the powerful monsoons of the Indian Ocean. They understood ocean currents as invisible rivers within the sea, using them to speed their journeys. This deep environmental knowledge allowed them to establish permanent trade routes, carrying precious cargoes of Mediterranean olive oil to Britain and returning with Baltic amber, or transporting Indian spices to Roman ports in exchange for gold and glass. The sail did more than move goods, it moved people and ideas. Greek philosophy, Egyptian mathematics, and Mesopotamian astronomy spread across the known world in the holds of sailing ships carried by traders and colonists. The Vikings, with their iconic longships and sophisticated square sails, used this technology not just for raiding, but for exploration, settling lands as far away as Iceland, Greenland, and even the coast of North America. By reducing the exhausting reliance on human rowers for long-distance travel, the sail made these epic journeys logistically possible. It allowed a single vessel, driven by the limitless power of the wind, to carry the cultural DNA of entire civilizations across the water. The slow evolution of the sail, from a simple square to the more efficient lateen rig, which allowed for better sailing against the wind, shows a continuous, global experimentation with aerodynamics. This ancient machine truly built our interconnected world, but just as the sail mastered the movement of ships across water, another rotating marvel was designed to move the water itself, not with a screw, but with the relentless power of a river's current. This brings us to the Noria, a machine that lifted both water and human spirits. A giant wooden wheel turns endlessly in the river, its empty clay buckets dipping beneath the surface only to rise moments later, full and spilling their contents into a stone aqueduct high above the bank. This is the Noria, a self-powered river giant that transformed flowing water into agricultural abundance. While the Archimedes Screw required a person to turn its handle, the Noria worked automatically, its paddles pushed by the current of the river itself. This was one of the ancient world's earliest examples of true automation, a machine that never tired, never slept, and required only the constant flow of the water to perform its vital work. These structures could be colossal, some reaching diameters of over 30 feet, lifting life-giving water to heights previously unimaginable for irrigation. They fed complex networks of channels that carried water to fields far from the river's edge, turning arid plains into verdant gardens. The Romans, ever the practical engineers, saw the potential of this technology beyond the farm. They adapted the Noria's principle for use in their deep mines, where multiple wheels could be arranged in sequence to lift floodwater from terrifying depths, and integrated them into urban water systems to supply public fountains and baths. This constant, reliable flow of clean water was a revolution in public health, reducing disease and improving the quality of life in crowded cities. The Noria was more than just a machine, it became a part of the cultural landscape. Its rhythmic, groaning turn and the gentle splash of its buckets provided a soundscape for rural life, a symbol of nature and human ingenuity working in harmonious partnership. Its design was so effective that it spread from its origins in the Middle East across the Muslim world and into Europe, influencing the development of later water-powered machinery for centuries. How did the Noria influence the water wheels that would one day power the mills of medieval Europe? It provided the foundational principle of harnessing a river's current directly for mechanical work, a concept that would eventually drive entire industries. Yet, for all its automated brilliance, the Noria was ultimately dependent on the whims of a river. For tasks requiring power on demand in any location, ancient civilizations turned to a more mobile, if demanding, source of energy. This brings us to the indispensable role of animal labor. The strength of 1,000 men could be found in the patient, steady pull of a single ox. Animals were the living engines of the ancient world, biological machines whose power was harnessed through brilliant mechanical interfaces. A team of oxen, yoked together and walking an endless circle, could rotate a massive millstone for hours, grinding grain into fine flour without a single human hand touching the stone. This was not just a scene from a rural past, it was the backbone of urban food supply. The Romans perfected this system, building large-scale animal mills or pistrina, where multiple horses or donkeys powered mills in vast, echoing halls, producing flour on an industrial scale to feed the teeming population of cities like Rome. This partnership extended far beyond the granary. With a properly fitted yoke, a pair of oxen could pull a plow through soil that would break a farmer's back, or haul a sledge bearing a multi-ton stone block for a new temple. The efficiency of this system, however, hinged on three critical elements: breeding, training, and the technology of control. Selective breeding produced stronger, more resilient animals. Generations of training taught them to respond to verbal commands and to walk steadily in repetitive patterns, but the true innovation was the harness. Early throat and girth harnesses were poorly designed, often choking a horse and drastically reducing its pulling power. The invention of the padded horse collar, which transferred the load to the animal's powerful shoulders and chest, was a quiet revolution. It effectively doubled the amount of work a single horse could perform, transforming transportation and agriculture across continents. This deep reliance on animal labor inevitably raises profound ethical questions that echo into our own time. Ancient societies viewed animals as essential partners, but also as property and resources, while some cultures, like those in India, integrated principles of respect and non-violence towards working animals, the daily reality was often one of hard labor and short lives. The very scale of their achievements, from the terraced mountainsides to the transported obelisks, was built upon this foundation of animal muscle. It forces us to reflect on the nature of progress itself and the costs that are so easily forgotten by history. As the sun traveled its daily arc, another machine was silently at work, one that did not rely on muscle but on shadow and light to bring order to human existence. A stone pillar's shifting shadow became the world's first clock. This simple, silent machine, the sundial, transformed the chaotic passage of daylight into a measured, predictable rhythm. Ancient civilizations from Egypt to Babylon to China looked up, observed the sun's unwavering path, and then looked down to etch its journey into stone. They realized the shadow cast by an upright gnomon would sweep across a marked surface in a consistent, daily arc. This was not just about telling time, it was about creating time as a shared, tangible concept. The true genius of these devices lay in their calibration. A sundial built for the flat plains of Mesopotamia would be utterly useless on the hilly terrain of Greece. Craftsmen had to possess deep astronomical knowledge, angling the gnomon precisely to match their latitude and scribing the hour lines to account for the sun's changing height in the sky across the seasons. This was applied mathematics made solid, a permanent record of celestial mechanics. This new structure imposed order on everything. The sundial dictated when markets would open and close, when civic meetings would commence, and when temples should hold their prayers. It turned the vague notion of midday into a specific communal event. For the first time, society could synchronize its activities on a scale larger than a single village. The design evolved beautifully over centuries, from grand public monuments to intricate, folding pocket dials carved from ivory that travelers could carry to manage their journeys. This portable timekeeping began to shift human perception from being purely tied to the land to being something an individual could possess and manage. But the impact of this precise timekeeping rippled far beyond daily schedules. How did the accuracy of sundials influence other fields like navigation and architecture? For sailors, understanding the sun's peak height was a crucial step in determining latitude at sea. For architects, the consistent solar path informed the orientation of temples and cities, aligning them with cosmic order and bathing sacred spaces in light on specific, significant days. The sundial taught humanity to read the sky not as a mystery but as a guide. It proved that the most profound machines often have no moving parts, only an elegant alignment with the laws of nature. This mastery of natural force through geometry finds a much more visceral expression in our next machine, a tool that concentrates immense pressure into a single, splitting point, the wedge. A single, sharp edge can accomplish what 1,000 blunt blows cannot. The wedge is a machine of pure force concentration, taking a broad, powerful push and focusing it onto a vanishingly thin line to split, cut, and shape the world. In the quarries that supplied stone for the pyramids, workers would laboriously drill a line of holes along the intended fracture line. Into these holes, they would drive dry wooden wedges. Then they would pour water over them. As the wood swelled with a slow, irresistible pressure, it would generate enough stress to cleanly split a colossal block of granite or limestone from the bedrock. This was not destruction, but precise liberation, a conversation with the stone's own hidden grain. The same principle was at work in the carpenter's workshop, where a metal wedge would be tapped into the end of a log to cleave it into perfect planks. The effectiveness of this entire process hinged on the wedge's angle. A long, shallow wedge would spread the force over a wider area, creating a controlled split ideal for wood. A short, steep wedge concentrated all the energy into a tiny point, designed for piercing and crushing. This understanding of geometry and material science transformed the wedge into one of history's most versatile tools. On the battlefield, it became the bronze tip of a spear designed to punch through leather armor or the deadly point of an arrowhead. In the kitchen, it was the stone axe that butchered game and the flint knife that carved wood. Even the humble nail is a variation on the wedge, using its tapered form to push aside fibers of wood and create a secure hold. Look around any modern workshop or construction site, and you will see the wedge's enduring legacy. Every chisel, every saw tooth, every drill bit, and even the blade of a common scissors operates on this ancient, fundamental principle of redirecting and intensifying force. It is a testament to a simple truth that the sharpest ideas often have the most cutting edge. And just as the wedge mastered the art of splitting and cutting, another simple device was revolutionizing the art of moving heavy loads across the ground, eliminating the grinding friction that made dragging stones an epic struggle. This brings us to the humble roller. A stone block weighing more than an elephant could glide across the desert as if on a conveyor belt. This was the everyday miracle of the roller, a solution of such elegant simplicity that it conquered the immense friction of the earth itself. Workers would place a series of sturdy, uniform logs perpendicular to the path of a massive stone slab resting on a wooden sledge. As teams pulled on ropes, the sledge would push the logs beneath it forward. A critical moment came as a roller emerged from the back of the load, where waiting hands would swiftly carry it to the front, creating a continuous, moving roadway of wood. This system transformed a brutal, grinding drag into a relatively smooth, rolling motion. The secret lay in how the cylindrical logs distributed the immense weight. Instead of one large surface scraping against the ground, the force was concentrated on the small, rotating contact point of each log, drastically reducing the resistance. For the Egyptians moving a 200-ton obelisk, this was not just a matter of efficiency, but of pure feasibility. To make the system even more effective, workers would often pour water or slick mud in front of the advancing rollers, creating a lubricated path that further eased the passage. This operation demanded incredible coordination. A foreman's chants or drumbeats likely synchronized the teams pulling the load and those racing to reposition the logs, a carefully choreographed dance of human and machine. The roller was a democratic technology used from the quarries of Egypt to the temple sites of ancient Greece and the road-building projects of the Romans. Its universal application proves a profound point that the most powerful innovations are often those that simplify a fundamental physical challenge. How did this constant repetition of rolling logs eventually inspire a more permanent solution? The natural evolution was to fix an axle between two rollers, creating a stable platform that no longer needed resetting, a concept that gave birth to the wheeled cart and forever changed transport. This brilliant method for horizontal movement finds its perfect counterpart in a machine designed for vertical ascent, the winch. A simple crank could lift a mountain of stone. The winch took the rotating power of the wheel and axle and focused it into a single, relentless task, hauling immense weight straight up into the sky. At its core was a cylindrical drum anchored to a sturdy frame. A rope was wound tightly around this drum, and when workers turned a handle, the crank, it would slowly and powerfully coil the rope, pulling whatever was attached to its other end upward. This was vertical ambition made real, but the true genius of the winch was revealed when it was paired with a pulley system. By threading the winch's rope through a set of pulleys fixed high above, engineers could multiply the lifting force exponentially. A team of 4 men turning a crank might then hoist a block of stone that would normally require 40 men to lift directly, a staggering tenfold increase in power. This combination was the secret to building upward on a scale never before possible. On the slopes of the Acropolis, Greek engineers used precisely this system to lift the massive marble blocks for the Parthenon, each turn of the crank raising civilization another inch toward the gods. The Romans, masters of practical application, employed winches in the construction of their colossal amphitheaters like the Colosseum, where they were essential for raising materials to the highest tiers and for operating the complex elevators and trapdoors that created spectacular effects during gladiatorial games. In military contexts, the winch was the heart of the ballista, a giant crossbow-like siege engine. Soldiers would use a winch mechanism to slowly, agonizingly draw back the weapon's heavy arms, storing immense energy in twisted sinew ropes before releasing a massive bolt that could shatter wooden gates. But with such immense power came immense danger. What safety mechanisms did ancient engineers incorporate into winch designs? The most crucial was the ratchet and pawl, a brilliant piece of insurance. The ratchet was a notched wheel attached to the drum. A spring-loaded metal bar, the pawl, would click against these notches as the drum turned. If the workers lost their grip or the rope strained under a sudden load, the pawl would catch instantly in a notch, preventing the crank from spinning backward and the load from plummeting to the ground. This simple device prevented countless catastrophes, allowing for controlled, safe lifts even with multi-ton stones swinging in the air. The operation itself was a symphony of coordinated labor. Teams of workers would push on long bars inserted into the crank, marching in a circle to the rhythm of a foreman's chant. This collective effort, the synchronized muscle of many, was what turned the machine. The winch's legacy is the skyline of the ancient world, a testament to what humanity can raise when we combine simple physics with unwavering cooperation. That same cooperation, harnessing force and wind, was essential for the next machine, one that breathed life into the forge and shaped the very metals that made the winch possible. This brings us to the bellows. A controlled breath of air could transform a simple fire into a crucible of creation. Bellows were the lungs of the ancient forge, a machine that gave human ambition the power to liquefy stone and reshape the very elements. The principle was one of forced draft. By compressing a leather bag, a blacksmith would blast a concentrated stream of air into the heart of a charcoal furnace. This oxygen rush supercharged the combustion, driving temperatures from a mere glow to a searing heat capable of melting metal ore. This was the fundamental breakthrough that separated the Stone Age from the ages of metal. Without this forced air, early furnaces simply could not reach the temperatures needed to extract pure copper from rock, let alone smelt the far more resilient iron. Early designs were simple, handheld bags, but the technology quickly scaled. Foot-operated bellows freed the smith's hands for manipulating the molten metal, while massive, industrial-scale versions were powered by water wheels or the patient tread of oxen, creating a continuous blast for large foundries. This mastery over heat did more than just produce metal, it defined the trajectory of civilizations. The ability to reliably smelt copper led to the alloying of bronze, a metal far harder and more durable, which gave rise to superior weapons, armor, and tools. But the bellows truly proved their worth with the advent of iron. Iron requires a significantly higher melting point than copper or bronze. It was the evolution of bellow technology, producing a hotter and more consistent blast, that finally made the widespread smelting of iron ore a practical reality. This transition from the Bronze Age to the Iron Age was not just a change in materials, it was a societal earthquake. Iron was more abundant and far cheaper than bronze, which relied on scarce tin. This democratized metalworking, putting stronger plowshares in the hands of more farmers and deadlier weapons in the hands of larger armies, reshaping economies and power structures across the globe. The influence of this precise temperature control extended beyond the smithy. In pottery kilns, bellows allowed for the firing of finer, stronger ceramics and the creation of early glazes. In glassmaking, they enabled the crafting of clear, durable vessels and brilliant art. The bellows represent a profound leap in our relationship with the natural world, a deliberate manipulation of a fundamental element to achieve an industrial outcome. This same mastery of rotation and pressure that fed the forge found a more delicate, yet equally transformative, expression in another machine that shaped both daily life and artistic culture. A spinning disc transformed a lump of clay into a perfect, symmetrical vessel with a single, continuous motion. This was the potter's wheel, a machine that did more than just shape pottery. It shaped economies and cultures. Its hum was the sound of civilization standardizing itself. Invented in Mesopotamia around 3500 BCE, the earliest versions were simple stone discs that the potter or an assistant would spin by hand. This was a start, but the true revolution came with the kick wheel. This design featured a heavy, lower flywheel connected by an axle to the spinning table above. The potter could use their foot to keep the flywheel in constant, smooth motion, leaving both hands completely free to coax the clay upward from a centered lump into a tall, thin-walled jar. This continuous rotation was the key to both speed and perfection. A skilled artisan could now produce dozens of identical bowls, urns, or storage jars in a single day, a rate of production that was previously unimaginable. This standardization was not merely about convenience, it was the foundation of complex trade. A merchant in Egypt could now agree to ship 100 units of grain to Greece, with both parties confident in the exact volume each jar would hold. Pottery became the universal shipping container of the ancient world, enabling the reliable transport of olive oil, wine, grains, and salted fish across the Mediterranean. But these vessels were far more than just functional containers. The smooth, rotating surface of the wheel became a canvas for artistic expression. As the pot spun, artists could paint intricate scenes with a steady hand, depicting everything from the daily routines of farmers to the epic tales of gods and heroes. This rotating motion allowed for the creation of precise, repeating geometric patterns that wrapped perfectly around the entire vessel, a hallmark of classical Greek pottery. The skill required to control this spinning force was immense. A potter had to develop an intuitive feel for the clay's moisture, the wheel's speed, and the exact pressure of their fingers, a knowledge that was honed over a lifetime and passed down through generations. This made potters highly respected artisans, their workshops vital hubs of both practical industry and cultural storytelling. So what cultural significance did this machine amplify? Pottery was the everyday art of the ancient world, present in every home, from the humblest cooking pot to the most elaborate funeral urn. It was used in religious rituals, buried with the dead to accompany them into the afterlife, and stored the very surpluses that allowed cities to flourish. The potter's wheel amplified this significance by turning a fragile, hand-built object into a durable, beautifully symmetrical symbol of a society's technical skill and artistic vision. It embedded culture into the very objects people used every single day. This same drive for order and measurement that standardized pottery also demanded a way to impose lines and boundaries upon the land itself, leading to the invention of a machine for dividing the earth. A straight road stretching to the horizon began with a simple cross of wood. The Groma was the master of right angles, the instrument that imposed geometric order onto the chaotic landscape of the ancient world. A Roman surveyor would plant its vertical staff firmly into the ground. From the ends of 4 horizontal arms, each aligned perfectly perpendicular, hung weighted cords called plumb bobs. By sighting past these vertical strings, the engineer could establish a flawless line in one direction, then pivot the device 90 degrees to mark another. This ability to create perfect right angles and parallel lines was the foundation of everything. It carved the sprawling countryside into neat, taxable plots of farmland for returning soldiers. It laid out the rigid, grid-like street plans of new colonial cities from Britain to North Africa, ensuring efficient traffic flow and military control. The legendary straightness of Roman roads, some stretching for thousands of miles, was a direct result of this tool, allowing legions to march and imperial messengers to travel at speeds that would not be surpassed for over 1,000 years. The surveyor who operated the Groma was more than a laborer. He was a geometer, a mathematician who translated theoretical principles into the very dirt and stone of the empire. His work required a steady hand, a keen eye, and the patience to ensure that the lines he set today would endure for centuries. How did the Groma's principles influence later surveying instruments and cartography? Its fundamental concept of establishing fixed lines of sight through suspended weights evolved directly into the more sophisticated dioptra and the astronomer's quadrant, tools that would later map coastlines and chart the stars. The Groma's legacy is the map itself, the very idea that the world could be measured, divided, and understood with precision. This need for exact measurement in dividing the land finds a parallel in the daily necessity of dividing the harvest, a task that relied on another ancient machine designed not for alignment but for grinding. Now we explore a machine that processed grain, the quern. The rhythmic scrape of stone on stone was the sound of survival in the ancient home. Two circular stones, the quern, transformed inedible kernels of wheat and barley into the fine flour that baked the daily bread. This was not a machine for monuments, but for the foundation of life itself. Its basic principle was one of immense pressure and abrasion. The lower stone, the meta, remained stationary. The upper stone, the catalyst, was rotated over it, its grooved surface grinding the grain trapped between them into a coarse meal. Early versions, known as saddle querns, required a back-and-forth pushing motion with a smaller handstone, a tedious and inefficient process. But the revolutionary leap came with the rotary quern. Here, a handle fixed to the upper stone allowed for a continuous, circular grinding motion. This was a dramatic improvement, yielding more flour in less time with significantly less physical strain. The efficiency of this simple machine rippled through society. It supported the rise of professional bakeries in growing cities, where larger, animal-powered querns could produce flour on a scale to feed thousands. A single donkey walking in an endless circle to turn a massive millstone could do the work of dozens of people with hand querns. This specialization meant that not every household had to dedicate hours each day to this fundamental task, freeing labor for other crafts and trades. Yet within the home, the operation of the smaller quern was often the relentless, daily burden of women and enslaved individuals. The physical toll was immense, leading to arthritis and chronic pain, a quiet testament to the social hierarchies that defined so many ancient civilizations. The quern was a symbol of sustenance, but also of the unequal distribution of labor that made that sustenance possible. So how did improvements in grinding technology affect diet and health? The shift from coarse, hand-pounded grain to finer, more efficiently milled flour was a nutritional revolution. Finer flour was more easily digested, allowing the body to absorb more calories and nutrients from the same amount of grain. It also led to the creation of lighter, more palatable breads, transforming the most basic staple from a hard, chewy sustenance into a versatile and central part of the diet. This technological refinement, born from the simple rotation of two stones, directly supported population growth and the vitality of entire cities. The Quern's evolution is a story written in flour and stone, a quiet machine that built the world one loaf at a time. Just as this device mastered the transformation of grain, another machine was designed for the essential task of moving water, relying not on a river's current but on the steady pace of human feet. This brings us to the Tympanum. A giant wooden drum turning slowly beside a river could lift water with the steady rhythm of a heartbeat. This was the Tympanum, an ancient water-lifting machine that functioned like a relentless, compartmentalized wheel. Its hollow interior was divided into 8 wedge-shaped sections, each one an individual bucket. As the drum rotated, these compartments would scoop up water at the lowest point of their journey. They would then carry this captured water upward, trapped securely inside, until they reached the very top of the rotation. There, gravity would take over, and the water would pour out through a carefully positioned spout directly into an awaiting aqueduct or irrigation channel. This sealed, compartmental design was its genius, minimizing spillage during the lift and ensuring a remarkably efficient and continuous flow. Unlike the Noria, which relied on the river's own powerful current to turn its massive wheel, the Tympanum was a machine of pure muscle. It was typically powered by a person or an animal walking on treads attached to its sides, a slow, plodding march that translated into a reliable hydraulic pulse. This made it the perfect solution for slow-moving streams or low-lying water sources where the current was too weak to drive a Noria. Ancient engineers built these devices from the most durable materials available, primarily thick, waterproofed wood, and reinforced with iron bands to withstand the constant stress of rotation and the relentless weight of water. The constant immersion and movement demanded robust construction, a testament to the practical understanding of materials needed to make innovation last. The Tympanum stands as a powerful example of engineering adaptation, a machine tailored to its specific environment. This principle of combining simple machines to solve complex challenges finds its ultimate expression in a device that reshaped the ancient skyline, the crane. A wooden skeleton rose against the sky, a framework of beams holding a complex dance of ropes and wheels. This was the ancient crane, a compound machine that pulled civilization upward. It was not a single invention, but a brilliant synthesis, integrating the lever's principle in its boom, the pulley's redirecting force in its sheaves, and the winch's relentless pulling power in its central drum. By combining these simple machines, Greek and Roman engineers created a device capable of hoisting multi-ton stones to heights that ramps alone could never efficiently reach. The true power of this system lay in its multiplicative effect. A single worker turning a winch with a rope threaded through a series of pulleys could exert a lifting force equivalent to a dozen men, all with controlled, precise movement. This mechanical advantage transformed construction from a sprawling ground-level effort into a focused, vertical ascent. The Romans then amplified this power with a new source of energy: human footsteps. Their treadwheel crane placed workers inside a giant wooden wheel, much like a hamster wheel. As they walked, their collective weight and motion turned the wheel itself, which acted as the winch's drum, coiling the rope with immense sustained force. This innovation was a powerhouse, allowing smaller crews to lift even heavier loads for longer periods. With the crane, architecture could truly defy gravity. It enabled the construction of Rome's multi-story apartment blocks, the insulae, which housed its vast population by building upward instead of outward. It was essential for positioning the massive stone arches and vaults of aqueducts and temples, locking them into place with a precision that ensured their survival for millennia. The entire operation, however, hinged on a delicate balance. The wooden frame had to be engineered to withstand tremendous stresses, and the load had to be carefully centered to prevent a catastrophic tip. The invention of the crane did more than just change construction techniques. It reshaped the urban skyline and architectural ambition. How did the invention of the crane influence urban development and architectural styles? It allowed cities to become denser and more vertical, supporting larger populations in a concentrated area. Architecturally, it encouraged styles that emphasized height and grandeur, with soaring columns and elaborate facades that proclaimed a society's technical prowess. This machine for lifting stone into the heavens relied on another to first cut it from the earth, a tool that bored into the bedrock itself, the drill. A single bowstring pulled back and forth could spin a sharp point deep into stone. This was the bow drill, a tool that mastered the power of rotation to bore holes with relentless precision. The design was brilliantly simple. A cord was wrapped around a vertical spindle with a drill bit fixed to its bottom end. The user pressed down on a handle atop the spindle while moving the bow horizontally, sawing the string back and forth. This motion spun the drill bit at high speed, its abrasive tip grinding away material through sheer friction. In the workshops of ancient Egypt, artisans used bow drills tipped with copper or hard stone to bore minute holes in beads of carnelian and lapis lazuli, threading them into intricate jewelry for the elite. For carpenters, the drill was indispensable for creating joinery. They could drill precise holes for wooden pegs or dowels, which would lock pieces of timber together without a single nail, forming the strong, flexible frames of ships, furniture, and roofs. This rotational action demonstrated a deep, practical grasp of material science. Workers understood that a constant, fast spin generated immense heat and abrasion, effectively wearing down a substance far harder than the drill itself through persistent, focused effort. But the drill's impact was felt most powerfully in the quarries. Here, heavy stone drills operated by multiple workers were used to perforate granite and limestone. They would drill a series of closely spaced holes along a desired fracture line. Into these holes, they hammered dry wooden wedges. Then they poured water over the wood. As the wedges swelled, they generated enough uniform pressure to split a colossal block cleanly from the bedrock. This method turned the chaotic process of quarrying into one of controlled, predictable liberation. The evolution of this machine is written in the history of its bits. How did the progression of drill bits reflect advancements in metallurgy? The earliest bits were merely sharpened flint or hardened copper, adequate for soft stone and wood but quickly dulling against tougher materials. The advent of bronze allowed for stronger, more durable tips that could hold a sharper edge for longer, but the true revolution came with iron and later steel. The ability to forge hardened iron drill bits transformed the tool's capabilities, allowing it to tackle the hardest granites and basalts with relative efficiency. This metallurgical leap directly enabled the creation of more complex objects, from the intricate locking mechanisms of doors and chests to the precisely drilled axle holes for chariot wheels and the tuned air columns of early flutes and pipes. The drill's legacy is one of hidden precision, the perfectly round hole that made grand assembly possible. That same need for meticulous, repetitive assembly finds a parallel in the next machine, one that wove separate threads into a single, durable fabric, the loom. A single thread holds no power, but thousands woven together could clothe an army and sail a ship across the sea. The loom was the machine that orchestrated this transformation, turning fragile plant and animal fibers into the very fabric of civilization. Its basic principle is a beautiful symmetry of tension and passage. Vertical threads, known as the warp, are held taut on a frame. Then, a horizontal thread, the weft, is passed over and under them, back and forth, building a sturdy textile one line at a time. Early looms were simple, little more than wooden frames that demanded incredible patience. But the true revolution came with the heddle, a brilliant device that lifted select warp threads simultaneously, creating a space, a shed, through which the weft could be passed in a single, swift motion. This simple rod, threaded with loops, automated the most tedious part of the process, allowing for complex patterns and dramatically faster production. The skill of the weaver then shifted from pure endurance to intricate design, lifting different combinations of threads to create stripes, checks, and eventually elaborate pictorial scenes. In the high Andes of ancient Peru, weavers used backstrap looms where one end of the warp was tied to a post and the other to a belt around their own body. By leaning back, they created the necessary tension, their own form becoming part of the machine. The textiles they produced were not merely cloth, they were a language. Intricate patterns and colors conveyed a person's village, social status, and even their spiritual beliefs, making fabric a wearable identity. The operation demanded a lifetime of skill, turning weavers into respected artisans whose work was essential to the economy. This was not a trade of luxury, but of absolute necessity. Loom-woven cloth provided protection from searing sun and bitter cold. It created sails that harnessed the wind for exploration and trade, and it produced the bags and sacks that stored and transported the food surpluses that sustained cities. The spread of loom technology from China to Egypt to the Americas created a shared industrial language. What role did textiles play in ancient economies and diplomatic exchanges? They were often a primary trade good, a form of currency, and a tool of statecraft. Fine Egyptian linen, colorful Phoenician purple wool, and soft Chinese silks were coveted across continents, given as royal gifts to secure alliances, and displayed as symbols of a nation's wealth and refinement. The value placed on these fabrics fueled entire industries, from shepherding and flax farming to dyeing and tailoring, supporting a complex chain of labor that formed the backbone of ancient commerce. This machine for weaving the threads of society finds a parallel in a device designed to move the very air we breathe, the fan. A simple leaf could command the very air itself. Long before the whir of electric motors, the fan was a master of fluid dynamics, a machine that turned simple motion into a life-giving breeze or a blast of industrial heat. In the sweltering heat of the Nile Delta, a servant wielding a broad palm leaf created a pocket of comfort for a noble. This was more than a gesture of luxury. It was an application of fundamental physics, using a broad surface to push a mass of air and accelerate its flow over human skin. But the fan's role extended far beyond personal comfort. In the bronze foundries of ancient China, workers operated large, mechanically driven fans, often powered by foot treadles or hand cranks. These devices directed a continuous stream of air into furnace chambers, supercharging the fire to reach the extreme temperatures required for smelting metal. This forced draft was the difference between a mere hot fire and a crucible of liquid bronze, a direct manipulation of the environment to achieve an industrial goal. The fan's principle was beautifully adapted for architecture as well. In ancient Persia, builders constructed wind-catching towers or bajirs, which functioned as massive, static fans for entire buildings. These tall, chimney-like structures captured the prevailing winds at their peaks, funneling the cooler, faster-moving air down into the living spaces below, while simultaneously drawing warm air up and out. It was a completely passive, brilliant form of air conditioning that transformed desert homes into oases of cool tranquility. How did the cultural significance of fans differ across civilizations? In China, exquisitely crafted hand fans made of silk and sandalwood became intricate symbols of status and refinement, their paintings and calligraphy reflecting the owner's education and taste. In Japan, the folding fan was a central element in ceremonial dance and theater, its precise movements conveying specific emotions and narratives. In contrast, the rigid fans of ancient Egypt were often associated with divinity and royalty, used in religious processions to honor the gods. This simple tool's design was a study in elegant efficiency, from fixed paddles that moved the maximum volume of air to ingeniously folding versions that could be tucked away, proving its incredible adaptability to both function and culture. This mastery over moving air was essential for comfort and industry, but it was matched by an equally vital need to master the movement of liquids, for storing and transporting the water, wine, and oil that fueled daily life. Civilizations turned to a machine of perfect form and function, the amphora. A ceramic jar with two sturdy handles and a tapered base did more than just hold wine. It built the economic network of the ancient world. The amphora was a packaging machine of brilliant design, a standardized container that made global trade possible long before the word global had any meaning. Its iconic shape was pure engineering. The pointed base was not a flaw, it was the key to its success. On a ship, these jars could be stacked tightly in the hold, nestled securely between ropes or in layers of sand, their bases fitting into the gaps between the necks of the jars below. This created a stable, interlocked cargo that could survive the violent pitching of a stormy sea. When it came time to unload, the pointed end allowed a worker to easily tilt the jar for pouring, or even to plant it upright in the soft earth of a warehouse floor. This was form and function perfected over centuries. Production was a marvel of ancient industry. Potters used molds and fast wheels to produce these jars in staggering numbers, creating a reliable, uniform product that could be traded by volume. Each jar was a piece of data. Stamps on the handles acted as early branding, indicating the estate that produced the olive oil, the region that bottled the wine, or the official who certified the measure. This built trust in a marketplace that spanned thousands of miles. The sheer volume of amphorae found by archaeologists tells a vivid story of ancient life. What do these broken pieces of pottery reveal about long-vanished trade routes? By analyzing clay composition and tracing those stamped marks, historians can map the flow of goods with astonishing precision. They can see Spanish olive oil reaching the docks of Rome, Egyptian grain feeding the cities of Greece, and fine wine from the Aegean Islands being traded for British tin. The amphora was the silent engine of this exchange, a humble jar that carried the flavors and fortunes of empires. This physical network for moving goods required a parallel system for managing the numbers behind it all, for counting the jars, calculating profits, and taxing the cargo. That need for calculation brings us to the next machine, one that gave merchants and clerks the power to handle vast sums with a few moving beads. A merchant's fingers fly across a wooden frame, sliding beads along rods with a rhythmic clatter. This was the abacus, the ancient world's calculating engine, a machine that brought order to the chaos of commerce. Its design was a model of elegant efficiency. Each column of beads represented a different place value, units, tens, hundreds, and so on. A lower bead might count as 1, while an upper bead represented 5. With practiced flicks of the wrist, a skilled user could add long columns of numbers, subtract costs from profits, and even perform complex multiplication and division at speeds that rivaled mental calculation. This was not a machine that thought for itself, but one that extended the mind of the person using it, providing a physical, fault-tolerant map of numerical relationships. Its invention is traced back to the counting boards of ancient Mesopotamia, but it was perfected independently across the globe. The Chinese developed the sophisticated suanpan, while the Romans used a portable version called the calculi with beads sliding in grooves. For a Roman tax collector assessing a farmer's grain, or a Chinese merchant negotiating the price of silk, the abacus provided an immediate, verifiable answer. It reduced costly errors in transactions and made the collection of taxes more accurate and efficient, which was the absolute lifeblood of imperial administration. Mastering this device required and cultivated formidable mental arithmetic skills. A user had to hold the problem in their head while manipulating the beads, a cognitive dance that made proficiency a clear mark of intelligence and education. The true genius of the abacus, however, lies in a concept so fundamental we now take it for granted. It demonstrated that physical objects could reliably represent abstract numbers. Each bead was a tangible symbol for a mathematical value, and the movement of those beads created a visual and tactile representation of a calculation in progress. This idea that the manipulation of physical states can model mathematical logic is the very bedrock upon which all modern computing is built. How did the abacus influence the development of written numerical systems? It provided a practical, daily framework for understanding place value, reinforcing the concept that the position of a digit determines its worth. This hands-on understanding likely paved the way for more sophisticated written numerals, moving beyond simple tally marks to the powerful systems we use today. In the flickering light of an evening market stall, the abacus was the sound of an economy at work, and it was another flickering light, steady and contained, that allowed that work to continue long after the sun had set. This brings us to the oil lamp. A single, steady flame pushed back the night, transforming darkness from an ending into an opportunity. The oil lamp was a machine for capturing time itself, a simple vessel of clay or metal that held burning oil fed by a wick. This controlled flame extended the day, allowing a craftsperson to continue weaving by its glow or a scholar to study scrolls long after sunset. Early versions burned whatever fuel was available, from rendered animal fat to olive oil, their light flickering but reliable. The design evolved with brilliant practicality, sprouting multiple spouts on a single lamp to create a broader, brighter pool of light that could illuminate an entire room. In the great libraries of Alexandria, countless lamps allowed knowledge to be copied and studied through the night, preserving texts that might otherwise have been lost. Within temple sanctuaries, their flames became symbols of eternal devotion, enabling rituals and prayers to continue uninterrupted by the setting sun. The lamp's operation relied on a subtle physical principle, capillary action, where the porous wick naturally drew the liquid fuel upward to feed the flame. This demonstrated an intuitive grasp of fluid dynamics, a quiet science in action every time a lamp was lit. For the first time, artificial light became a tool for safety and social order in crowded cities, its glow deterring crime and allowing people to gather safely after dark. How did the availability of artificial light affect social and economic patterns in antiquity? It fundamentally restructured the day. Artisans could increase their output, shops could remain open longer, and civic meetings could extend into the evening, fostering a more dynamic and productive society. This mastery over light, however, was matched by an equally vital need for precision in commerce, for ensuring that a measure of grain or a weight of silver was exactly as promised. This demand for fairness and accuracy brings us to the next machine, the balance scale. A simple beam and two suspended pans measured more than just weight, they measured fairness itself. The balance scale was the silent guardian of trust in the ancient marketplace, a machine that turned the abstract concept of justice into a physical, undeniable reality. Its principle was one of perfect equilibrium. A central fulcrum supported a horizontal beam from which two pans hung at equal distances. When the weight in both pans was identical, the beam rested level, a visual declaration of balance. This simple act of comparison was the foundation of commerce. In the gold markets of ancient Egypt, meticulous weights were placed in one pan while gold dust or rings were carefully added to the other, ensuring a pharaoh received his full due and a merchant was not cheated. In a bustling Roman forum, this same device would measure out exact portions of grain, olive oil, or spices, its impartial swing allowing trade to flourish between strangers. But the scale's influence reached far beyond the market stall. In the workshops of metallurgists, it was essential for alloying bronze, weighing precise amounts of copper and tin to create a metal of consistent strength and quality. In early pharmacies, healers used tiny scales to measure potent herbs and minerals, where a slight imbalance could mean the difference between a cure and a poison. This demand for precision required master crafters to build the scales with impeccable symmetry. The beam had to be perfectly balanced when empty, and the pans had to be of identical weight, lest the machine itself introduce a bias that would corrupt every transaction. Governing authorities understood this power, and they standardized the system of weights, often made of stone or bronze, and stamped them with official seals. These certified weights were the law made physical, a tangible promise that a pound of flour in one city was the same as a pound of flour in another. This daily use of the scale embedded deep mathematical thinking into ordinary life. Merchants and customers alike engaged with concepts of equivalence, proportion, and equilibrium every time they watched the beam settle. How did the use of scales influence legal systems and economic regulations? The scale became the ultimate symbol of impartial judgment. From the Egyptian belief that the god Anubis weighed a person's heart against the feather of truth in the afterlife, to the Roman goddess Justitia who held her scales aloft, the machine was a universal metaphor for moral balance. Legal disputes over inheritance or debt were settled by its objective measure, and tax collection relied on its accuracy to fund empires. The balanced scale taught humanity that for society to function, there must be a constant, verifiable standard against which all things are measured. This profound desire to measure our world did not stop at the marketplace or the courtroom. It soon reached upward toward the heavens themselves, in a quest to map the stars and track the passage of time with a device of stunning geometric beauty, the Astrolabe. A brass disc etched with the patterns of the cosmos could tell you precisely where you stood on the Earth and what time it was under the stars. This was the Astrolabe, a portable observatory that placed the universe in the palm of a scholar's hand. Its design was a masterpiece of layered geometry. The main plate, or mater, held a fixed map of the sky for a specific latitude, showing the horizon and the paths of key stars. Rotating atop this was the openwork retere, a delicate web of pointers representing the brightest stars and the ecliptic path of the sun. By suspending the instrument and aligning its sighting rule with a known star like Polaris, a user could spin the retere to match the current sky. Instantly, the device would reveal the local time, the position of the sun, and the ascendant sign for astrology. For a ship's captain on the dark, featureless sea, this was nothing short of miraculous. It transformed celestial navigation from an educated guess into a calculated science, allowing vessels to venture farther from familiar coastlines and establish reliable trade routes across the Indian Ocean and the Mediterranean. The creation of an astrolabe demanded a fusion of art and science. Master engravers spent months carving the complex stereographic projections onto the brass, a task requiring deep understanding of spherical astronomy. This was not a tool for the common person, but for the elite of intellect, navigators, and astronomers whose work expanded the very boundaries of the known world. How did the astrolabe's design vary across cultures, and what innovations did it inspire? In the Islamic world, where astronomy flourished, artisans produced exquisite versions with additional plates for different latitudes and specialized scales for prayer times. These sophisticated instruments directly influenced the development of the mariner's astrolabe, a heavier, simpler version designed to withstand the pitching deck of a ship, and later the refined quadrant. The astrolabe's true legacy is the idea that the heavens are a clock and a map waiting to be read. This same drive to process and refine, to extract essential value from raw materials, was at work back on solid ground, in the groves and mills that produced the lifeblood of the ancient economy. This brings us to the machine that crushed olives, the Trapetum. 2 stone wheels, each taller than a person, rolled slowly around a massive circular basin, their weight pressing a harvest of olives into a glistening green paste. This was the Trapetum, the machine that turned a simple fruit into the liquid gold of the Roman world. Its design was a masterclass in controlled force. A central vertical post anchored the device, while a long horizontal beam, acting as a giant lever, extended out to turn the 2 heavy crushing stones. As workers or animals pushed the beam in a continuous circle, the stones rolled around the basin, applying immense pressure to crush the olive flesh. But the true genius was in the basin's shape and the careful gap between the rollers and the central column. This gap was precisely calibrated to crush the soft fruit without shattering the hard pits inside. Shattered pits would release bitter tannins, ruining the oil's delicate flavor. The Trapetum ensured a smooth, first-press oil of the highest quality, a staple on every Roman table. This was not a small-scale operation. Constructed from durable, non-porous lava stone, the machine was built to last for generations and easy to clean, maintaining the strict hygiene necessary for food production. Its efficiency created a continuous workflow, transforming back-breaking manual pounding into a steady, industrial process. But what social and economic impacts did this machine create? Olive oil was more than just food, it was the lifeblood of the empire. It lit the lamps in homes and temples, fueled the public baths as a cleaning agent, and was a base for perfumes and medicines. Its production fueled a vast economic network, from the sprawling olive groves in North Africa and Hispania to the bustling port of Rome. The wealth generated built the villas of the elite and funded public works, while the oil itself was a form of currency, used to pay soldiers and civil servants. The humble Trapetum, therefore, was not merely a tool for crushing fruit. It was an engine of commerce, culture, and daily survival. Just as this machine refined a harvest from the earth, another device was designed to move the earth itself, reshaping the very land to suit human need. This was the scraper. A simple blade dragged across the earth could reshape the world for planting and building. The scraper was a machine of pure, elegant function, a flat plate of wood or metal pulled by a team of oxen. Its job was to level uneven ground, scrape away topsoil to create a firm foundation, or carve shallow irrigation ditches to guide precious water to thirsty crops. In the river valleys of ancient Mesopotamia, this tool was indispensable. Before a single seed could be sown, the scraper prepared the seedbed, creating the smooth, manageable surface that maximized the reach of water and the growth of grains. For construction, it was the first step in creating order from chaos, scraping a building site down to stable subsoil to support the weight of a temple or a palace wall. The evolution of its blade from a thick wooden board to a sharpened bronze or iron edge was a quiet revolution. A metal blade could cut deeper into compacted earth, move more soil with each pass, and withstand years of grueling work without splintering. This increased efficiency directly translated to scale. a community could now manage larger fields and undertake more ambitious building projects because the sheer physical labor of preparing the land was no longer an insurmountable barrier. The entire operation, however, was a delicate partnership. A farmer or laborer had to guide the scraper's handles with a steady pressure, controlling its depth and angle, while simultaneously directing the oxen with voice commands. This coordination between human intelligence and animal strength was a skill honed over a lifetime, a perfect example of interdisciplinary knowledge in action. How did the use of scrapers contribute to soil conservation and water management? By creating precisely graded fields and channels, the scraper helped prevent the uncontrolled runoff that washes away fertile topsoil. It allowed farmers to direct water exactly where it was needed, conserving every drop in arid regions and preventing waterlogging in others. This careful shaping of the land was a form of long-term thinking, a way of working with the environment to ensure its continued bounty. After the scraper had prepared the earth, the next challenge was to build upward from that foundation, a task that required a different kind of genius, one that could make stone float on air. This brings us to the corbel. A stone seems to float in midair, each block locked in a silent, gravitational dance. This is the magic of the corbel, an architectural technique that built ceilings and arches without a single drop of mortar or a piece of metal. Builders would stack stones or bricks in courses, with each layer projecting slightly beyond the one beneath it. Slowly, painstakingly, the two sides of a wall would reach toward each other, the gap narrowing until a final capstone could bridge the space, creating a perfectly stable, enclosed void. The entire structure was held together by nothing more than precise geometry and the relentless pull of gravity. In the soaring vaults of Mycenaean tombs like the treasury of Atreus, this method created monumental, beehive-shaped chambers that have stood undisturbed for over 3,000 years. Across the ocean, Mayan architects used corbeling to construct the narrow, towering roofs of their sacred temples, the stepped ceiling rising like a stone staircase to the heavens. The secret to its incredible durability was all in the cutting and placement. Every stone had to be shaped to exacting standards, its weight calculated, and its center of mass perfectly aligned so that the immense forces were channeled downward through the structure's walls rather than outward. A single miscalculation, one block cut a fraction too short or too long, could compromise the entire vault, leading to a catastrophic collapse. This was architecture as a high-stakes puzzle, where the solution was written in the laws of physics itself. How did corbeling influence the development of true arches and vaults? The corbel was, in essence, a stepping stone, a brilliant but structurally limited precursor. Its stepped profile created a lot of unnecessary weight and thrust. The revolutionary leap was the true arch with its uniform, wedge-shaped voussoirs. This new form channeled weight more efficiently into supporting piers, allowing for wider, taller, and more graceful openings. The corbel taught builders how to span space, and the arch showed them how to do it with breathtaking elegance. As we approach the end of our journey through these ancient machines, their collective legacy comes into sharp focus. The same invisible forces that lifted pyramid stones now power the cranes shaping our modern skylines. Ancient machines were not replaced, they were refined. The lever's principle is alive in the hydraulic arm of an excavator. The pulley's redirecting force operates in the elevator that carries you dozens of stories high, and the wheel's rotation spins the turbines that generate electricity for entire cities. This is not a coincidence, it is a direct inheritance. The foundational physics of mechanical advantage discovered millennia ago remain the absolute bedrock of every engine, gearbox, and computer we build today. Consider the simple gear, a direct evolution of the wheel and axle. While we did not explore it in detail, its concept emerged from the need to transfer and multiply rotational force between machines, a principle now essential in everything from a humble bicycle to the most advanced robotics. Ancient engineers were the first material scientists, pushing wood, stone, and bronze to their absolute limits. They learned through trial and error which woods could bear immense tension, how to shape stone to withstand compression, and how to alloy metals for greater strength. This relentless pursuit of material perfection established the very discipline that now gives us carbon fiber and superalloys. Perhaps their most profound lesson lies in their relationship with energy. These machines were overwhelmingly powered by renewable sources, human muscle, animal strength, flowing water, and the wind itself. They operated within the energy budget provided by their immediate environment, a masterclass in sustainable design that we are only now, with our concerns over fossil fuels, fully relearning. By studying their inventions, we are not just admiring relics, we are consulting a vast library of ingenious solutions. Their legacy is a powerful reminder that true progress does not erase the past, but stands firmly upon its shoulders, building on the discoveries of those who came before. Their creativity in the face of limitation challenges us to think differently about our own resources. How can we apply this ancient wisdom to the urgent challenges of sustainable development today? Could the passive cooling of wind catchers inspire new forms of energy-efficient architecture? Might the water-lifting principles of the Noria and the Screw find new life in low-impact irrigation for arid regions? The journey through these 34 marvels closes not with an ending, but with an invitation. It invites us to look at the modern world and see within it the enduring echo of the ancient, a testament to the timeless and universal language of human ingenuity. Our journey through time reveals a profound truth, that human ingenuity needs no microchips or engines to achieve the impossible. From the simple lever that moved mountains of stone to the complex crane that lifted entire cities toward the heavens, these ancient machines were born from a deep and patient observation of the natural world. They were not the products of sudden, magical discovery, but of generations of experimentation, of learning from failure, and of countless anonymous hands collaborating on a shared vision. These stories whisper to us across the centuries, reminding us that creativity is our most timeless resource, a universal language capable of overcoming any obstacle with nothing more than a fundamental principle and the will to see it through. When you gaze upon a modern skyscraper or a massive bridge, remember the foundations laid by those first engineers who taught us how to build. Their legacy is not just in the stone and wood they shaped, but in the very mindset of innovation they embodied. We would love to hear which of these ancient marvels captured your imagination the most. Was it the self-powered river giant, the Noria, or the deceptive strength of the compound pulley? Share your thoughts in the comments below. If you enjoyed this exploration into the roots of human achievement, subscribe for more journeys that uncover history's greatest mysteries. Thank you for watching, and may we always remember to look to the past for the inspiration to build a better future.